This is The Critical Thinker, episode 14. Hi, everyone. This is The Critical Thinker podcast, and I'm your host, Kevin Delaplante. I'm currently Associate Professor of Philosophy and Chair of the Department of Philosophy and Religious Studies at Iowa State University. I run a critical thinking tutorials website called The Critical Thinker Academy, which you can find at www.criticalthinkeracademy.com. The Critical Thinker podcast is a separate standalone production, but it's also meant to complement the material in the Critical Thinker Academy. This podcast is where I get to explore what it means to be an independent critical thinker, and I talk about the tools and concepts that are important if your goal is to improve your critical thinking skills. In episode 12, I talked about cognitive biases, what they are and why they're important. In that episode, I gave an example of a cognitive bias, known as the anchoring effect, or the anchoring bias. And I showed how this bias might be used by someone like a public relations advisor or a spin doctor to manipulate your beliefs and your behavior. The specific example I used involved a government advisor who uses the anchoring effect to help influence the public's perceptions of the severity of a military strike. Now, this example illustrated one of the reasons why learning about cognitive biases is important for critical thinking. The reason is this: more and more people in the influence industry, whose job it is to influence what you believe and how you act, are coming to understand how cognitive biases work and are using this knowledge to plan and execute their influence campaigns. So, if one of our goals as critical thinkers is to reduce our susceptibility to this kind of manipulation, then as a starting point at least, we need to learn something about cognitive biases and how they work and how they're actually used to influence our behavior. So that's one reason. This is analogous to the rationale for learning about logical fallacies as part of logical self-defense. We need to be able to discern good from bad reasons for belief. Now, in this episode, I want to look at another reason for learning about cognitive biases. This reason has to do with a more theoretical question, and one that I know is close to the interests of many of the listeners of this podcast. The question is simple: what is science? And more specifically, what is the essence of modern scientific methodology? This is an old question. It's a philosophical question. It's a question about the basis and rationale of the scientific method. It's also a contentious question. People disagree about what science is and what its methods are. If you're familiar at all with the philosophy of science literature or the science studies literature, then you know that there's a lot of debate about these questions. And there's a debate about a whole family of related questions like, is science objective? And what reason do we have to think that science gives us a more accurate picture of the world than any other worldview or belief system? And is there even such a thing as the scientific method? Now, I don't presume to settle these big questions in a podcast episode. At some point in the future, I'll do a whole course in the Critical Thinker Academy on philosophy of science issues, but my goals for this episode are much less ambitious. What I want to focus on is that last question. Is there such a thing as the scientific method? And I want to talk about the relevance of cognitive biases for this question, and what this means for the authority of science. So, is there such a thing as a scientific method? Scientists seem to think so. At least science textbooks seem to think so. If you open a high school or university science textbook, you'll often see a first chapter that discusses the nature of science and scientific reasoning. You might even see little flowcharts that are supposed to encapsulate the scientific method. Just Google the scientific method and look at the results under images. You'll see what I mean. But if you look at the history and philosophy of science literature, and you look across the full range of natural and social sciences, the picture is very different. What you see is a variety of scientific methods used within specific fields, but no single method that is common to all the sciences. And you also see, not always, but often, a considerable gap between the idealized textbook descriptions of scientific methodology and the actual processes, the actual histories that lead up to the adoption or rejection of a theory within a scientific community. Now, these observations lead some people to talk about the scientific method as a kind of institutionalized myth, a story we tell ourselves about how science works, but that doesn't really correspond to the reality. And it leads some to challenge the objectivity and authority of science, to challenge the presumption, so common in the developed West, that scientific knowledge is superior to other forms of knowledge, that the modern scientific worldview gives our best, truest description of the workings of the natural world. Now, for those who want to defend the superiority of scientific knowledge, the philosophical challenge is how to argue for this without defaulting to the naive mythic view of science and scientific reasoning that has been so thoroughly debunked by scholars. I admit that as a philosopher of science, I'm in this camp. This is a challenge for me. I cringe when I hear pro-science types make broad pronouncements about how science works. Science is about the search for universal laws. Science is about causal explanation. Science is about testing hypotheses that make falsifiable predictions. You can find exceptions to all of these without looking very hard. Yet I still think there's something special about scientific knowledge, something distinctive that gives it a privileged status. I don't think this is a trivial position to defend. I think the criticisms of the traditional view of science need to be taken seriously. What I do think, and this gets us to the main point of this episode finally, what I do think is that an understanding of cognitive biases can give us a really useful perspective on this question. It can help us think about why science is important and why scientific methods are what they are. Okay, with all that build-up, you'd expect that what I have to say about science and cognitive biases is going to be really deep and sophisticated. But it's not. It's really pretty simple. It can be summarized in 2 points. 1, human beings are prone to biases that lead to error. 2, scientific methodology aims to neutralize the effects of these biases and thereby reduce error. Okay, let's look at these 2 points in order. First, human beings are prone to biases that lead to error. What sorts of biases? Well, there are lots. I'm thinking of 2 kinds of biases in particular. The first is related to the fact that we're pattern recognition machines. Human beings see patterns everywhere. We're bombarded by sensory data, and our natural disposition is to seek out patterns in the data and attribute meaning to those patterns. An obvious example of this is our tendency to see faces in anything that remotely resembles the configuration of features on a human face. An electrical outlet looks like a face. The front grille of a car looks like a face. The knots of a tree look like a face. The back of an alarm clock looks like a face. Now, it's not surprising that we see faces everywhere. Face recognition is important for social primates like us. It's very important that we learn to read the facial cues of other people to know whether they're friendly or a threat, whether they're content or displeased, and so on. So we've evolved this very specialized and sensitive mechanism for facial recognition, and as a result, we're basically hardwired for it. But this means that we're prone to a certain kind of error as well, where we see faces in inanimate things that don't really have faces. And this is just one kind of pattern recognition mechanism working in our brains. There are lots of different kinds working all the time, looking for patterns that might be meaningful and imposing meaning on those patterns if they trigger the right cues. Michael Shermer calls this feature of our mental functioning patternicity. Now, in general, our ability to identify patterns is an extraordinarily valuable tool. It's essential for survival, for extracting meaningful, relevant information from our physical environment and from our social environment. But there's a price we pay for this amazing ability. Sometimes we attribute meaning to patterns which they don't have. And sometimes we see patterns in what is actually patternless noise. And it can be hard to not see these patterns when we expect to see them. Our expectation, or the subconscious workings of our brain, can sometimes impose a meaningful pattern on data or on sensory experience, even when there's nothing there. Psychologists have a bunch of names for this phenomenon. For visual images, like seeing faces in clouds, or the Virgin Mary on a slice of burnt toast, it's called pareidolia. The general phenomenon is called apophenia, which is defined as the experience of seeing meaningful patterns or connections in random or meaningless data. Let me show you a fun example. Have you ever heard of backmasking? This is when you play an audio recording backwards. Usually these are songs, and you hear meaningful speech when it's played backwards. When you do this deliberately to an audio recording, it's called backmasking or backward masking. It was controversial in the 1980s when a number of Christian groups in the United States claimed that heavy metal rock bands were intentionally putting satanic messages into their songs, which people could hear if they played the songs backwards. And what's interesting about backmasking is that people will often hear meaningful words or phrases in songs that are played backwards, even when they were never intentionally put there. And the effect is amplified when you're given some cues about what to look for in the audio. The very best place on the internet to experience this effect is Jeff Milner's backmasking site at jeffmilner.com/backmasking. For demonstration purposes, I'm going to play you a short sample from Jeff's site. First, I'll just play the audio in the forward direction, then I'll play it backward and see if you can make anything out of it. Okay, here's the first one. It's from a Britney Spears song. Okay, now listen to it backwards. Did you make anything out of that? Okay, now for those watching on video, read this text. Got it? Now listen. It's different this time, isn't it? Okay, for those listening just on audio, the text reads, "Sleep with me, I'm not too young." Now listen. And for good measure, I'll play it one more time. Now, notice that when you were primed with the suggested lyrics, you can't not hear those lyrics in the audio. But trust me, Britney Spears didn't intentionally backmask those lyrics. This is meaningless noise being interpreted as meaningful information, and we're all prone to it. And no amount of mental effort can make you not hear those lyrics. So, what does this have to do with science? My general point is that we're hardwired to see patterns in data and in observable phenomena. Sometimes these patterns are meaningful and point to underlying regularities. If they're regular, repeatable regularities, then we've got the basis for a predictively useful scientific generalization. Our knowledge of the basic laws of nature begins with identifying these basic patterns in observable data. But sometimes these patterns are not meaningful. Sometimes they're just noise. But we mistake them for meaningful patterns. This is an error, but it can be hard to see the error or correct for the error, especially if we're really invested in the reality of those patterns. Now, one thing that scientific methodology offers us is a set of tools for distinguishing meaningful from meaningless patterns. These tools come in different forms, but the obvious ones are the standard protocols for controlled experimental studies and statistical analysis of data from those studies, the stuff you would learn in a good research methods class in a science department. I'm not going to elaborate on those methods here, but ideally that's one of the things you end up learning in those courses, how to distinguish meaningful from meaningless patterns. So that's the first kind of error that we're prone to. The second kind of error that we're prone to has to do with how human beings are naturally disposed to weigh evidence, and more specifically, how we weigh evidence as it bears on the truth or falsity of a hypothesis. The general error is this: if we think the hypothesis is true, or would like it to be true, then we tend to remember or focus only on the evidence that would count in favor of the hypothesis, and ignore or dismiss evidence that would count against it. The result is that we build up a set of data that is lopsided in favor of the hypothesis, that is biased toward confirmation. That's why this phenomenon is called confirmation bias. And there's a huge psychological literature on this. Actually, confirmation bias can refer to a cluster of related phenomena. You can have bias search for information. This is where people test hypotheses in a one-sided way, by only searching for evidence that's consistent with the hypothesis that they happen to hold. They ask, what would you expect to see if this hypothesis was true? And look for evidence to support this prediction, rather than ask, what would you expect to see if this hypothesis was false? And look for evidence that would falsify the hypothesis. Then there's biased interpretation of evidence. This is where you give two groups the same information, the same evidence, but they interpret the evidence differently depending on their prior beliefs. So if you strongly believe some hypothesis, then you'll be inclined to think, for example, that studies that support that hypothesis are well conducted and convincing. But for studies that don't support your hypothesis, you'd be inclined to think that they're not well conducted and not convincing. One way to think of this is that people set higher standards of evidence for hypotheses that go against their current expectations, and they have lower standards of evidence for those that support their expectations. A third form of confirmation bias involves biased memory. Even if someone has gone ahead and tried to collect evidence in a neutral, unbiased way, they may still remember it selectively. So you end up recalling more of the confirming evidence than the disconfirming evidence, and it skews the evidence in favor of your expectations. I want to emphasize that these biasing effects I'm describing are well documented in the cognitive science literature. It's part of the cognitive biases literature that goes back several decades now, and it's an ongoing area of research. I'll have some references in the show notes for those who want to follow this up. Okay, so what's the upshot of this for our understanding of science? The upshot is that, left to our own devices, human beings are prone to error in the weighing of evidence. What's the error? The error is thinking that we're making a judgment based on a complete body of evidence, when the body of evidence we're considering has actually been filtered and skewed by confirmation bias. And that's going to lead to error in judgments about how well supported a hypothesis actually is. And this is where scientific methodology comes in. The physicist Richard Feynman once said that science is what we do to keep us from lying to ourselves. And I think there's a lot of truth to this. One of the functions of scientific methodology is to neutralize the effects of confirmation bias by forcing us to search for and weigh a complete body of evidence, one that includes not only confirming evidence but also disconfirming evidence, evidence that would count against the hypothesis in question. Let me give you a simple example to illustrate. Let's say you walk into a healthcare clinic and you see a flyer for a psychotherapist practice. The flyer says that Dr. Jones has a 90% success rate in treating mental health problems. You read a little more closely and it says that of all the patients he sees who come into his clinic complaining of psychological or mental health problems, 90% of them report an improvement in their condition within 2 weeks of beginning treatment with Dr. Jones. Now, for the sake of argument, let's assume this figure is accurate. If 100 people walk through his door suffering from some mental health problem, then if you survey them 2 weeks after beginning treatments with Dr. Jones, roughly 90 of them will say that their condition has improved. Here's the first question. Does this evidence support the conclusion that Dr. Jones's treatment is causally responsible for the improvement in their condition? Now, I know from experience that if I asked my science students this question, about 1/3 will say that it does support this causal hypothesis, and about 2/3 will say no, it doesn't. Because they've been told many times in their psychology classes that correlation does not imply causation. Maybe there's some other factor involved that's responsible for the correlation. Maybe it's the placebo effect, whatever. I think a survey of the general public would give a much stronger result, with a lot more people thinking that this evidence supports the claim that Dr. Jones's treatments are causally responsible for the improvement in condition. Now, what if I ask this question? Let's grant that the correlation doesn't necessarily imply causation. But does the evidence given even support the weaker claim of correlation? Does the fact that 90% of patients report improvement of conditions support the claim that there's at least a correlation between Dr. Jones's treatments and the improvement in their condition? And by correlation, all I mean is that if you go to Dr. Jones's clinic with a mental health problem, you're statistically more likely to report improvement in your condition than if you didn't seek out treatment. Now, if I ask this question to my science students, almost all of them will say that the evidence supports some kind of positive correlation. When I ask how strong a correlation, more than half will say that it's 90% or close to 90%. That you're 90% more likely to report an improvement in your condition if you go see Dr. Jones. Now, for those of you playing along at home, what do you think the answer is? Would you be surprised to hear that this evidence doesn't even support a claim of correlation at all? In fact, it gives us no reason to think there's any kind of correlation whatsoever, much less a 90% correlation. Okay, why is this? It's because we're only looking at confirming evidence. We have no information about potentially disconfirming evidence. To establish a correlation between Dr. Jones's treatments and improvement in condition, we would need to compare at least two numbers. The probability that a person will improve if they seek out treatment with Dr. Jones, and the probability that they will improve anyway on their own without seeking treatment from Dr. Jones. If it turned out, for example, that 90% of people will report improvement in their mental health problems within 2 weeks anyway without seeking treatment, then your odds of improving are the same whether you see Dr. Jones or not. And the correlation is zero. There's no positive correlation at all. Or maybe there's an 80% rate of improvement without treatment. So if the rate of improvement with Dr. Jones's treatment is 90%, then at best that would support a weak positive correlation of 10%, which is still very different from a 90% correlation. So this evidence in Dr. Jones's flyer, even if it's all 100% accurate, not only does it not support the hypothesis that his treatments are the cause of the improvements in his patient's condition, it doesn't even support a correlation of any kind between his treatments and improvement in his patient's condition. There just isn't enough information to justify these claims. But almost none of my science students, when they're given this hypothetical case, will see that this is the case. Most will say that the evidence supports a very strong correlation. This is because they're looking at an incomplete body of evidence and drawing a hasty inference, but they don't realize it until it's pointed out to them that the evidence is incomplete. Now, this is a very simple example, but it helps to illustrate the general takeaway point, which is that on our own, we suck at weighing evidence. And that highlights the function and the value of statistical methods and scientific protocols. They force us to seek out and take into consideration types of evidence that are relevant to the truth of the hypothesis, but that we would otherwise ignore or dismiss or downplay due to confirmation bias. Now, I've been focusing on confirmation bias here because I think it's particularly important, But of course, it's not the only source of bias in science. There are lots of them. But they just highlight the general point. In sciences that deal with living subjects, for example, there are biases that can result from expectation effects, like the placebo effect, where the mere expectation of a treatment will elicit a physiological response from a test subject. You can correct for this kind of bias by using blind randomized control groups, where subjects don't know whether they're receiving a treatment or just a placebo. So you can estimate the size of the placebo effect and use that to estimate the effect size due to the treatment itself. And there are also experimenter effects, where the experimenter's knowledge and expectations can unintentionally influence how subjects respond and how observations are interpreted. You neutralize these kinds of biases by using double-blind studies, where the researchers who directly interact with subjects and do data analysis don't know whether a given subject is in the test group or the control group. The point is that all these protocols are in place because human beings are prone to error, and we need these protocols to neutralize or correct for these errors. Okay, I'd like to wrap up this episode with a final comment on the bigger question that motivated this topic in the first place. The question was whether there is a way of defending the superiority of science as a source of knowledge about the world without resorting to a mythic view of how science works. I think the answer is yes, but it's a qualified yes. I think it's clear that if we didn't follow these scientific protocols, our knowledge of the world would be less reliable than it is. And it's clear why this is so when you think of these protocols as methods for neutralizing the effects of cognitive biases. But of course, this doesn't mean that scientists always follow these protocols. Science is a complex social practice. There are lots of things that can interfere with or prevent these protocols from being properly implemented. The highest quality studies are often the most expensive studies to conduct, for example, so funding can be a limited factor. The highest quality studies might also take many years, maybe even decades to conduct, so time constraints can be another factor. And in some fields, proper control studies might just be impossible to conduct. In genetics, for example, there are experimental ways of measuring the heritability of a trait, which is the percentage of the variation in the trait that can be accounted for by genetic variation in the population. You can do controlled experiments to directly measure heritability in fruit flies, but you can't do them on human populations because they would be unethical to conduct. So for humans, we're forced to rely on more indirect methods of estimating heritability that are more limited and more vulnerable to biases. So I admit that in some ways, this discussion of scientific methods still has an air of mythology about it, in the sense that it sets up an ideal that may never be perfectly realized in practice. But on the other hand, we still retain a notion of what makes science special, namely that it's an institutionalized social practice that is committed to these ideals, that strives to reduce the distorting effects of biases when it can. And in this respect, it's distinctive. There's no other social institution that functions quite the same way. When I talk about science in this way, my students sometimes think that I'm defending a mythic view of science as value-free, as though science, when it's properly conducted, doesn't make any subjective value judgments or is free of value biases. But that conclusion doesn't follow. What this view entails is that scientific methodology is committed to the elimination of certain kinds of biases, namely those that are conducive to error in the identification of meaningful patterns and in the weighing of evidence. But that's only part of what science is about. Science is very much a value-laden enterprise, and good science is just as value-laden as bad science. What distinguishes good from bad science isn't the absence of value judgments. It's the kind of value judgments that are in play. But I admit this is a big topic, and that's a subject for a whole other podcast. The other comment I want to make is that accepting this view of the scientific process still leaves open most of the big philosophical questions about the nature of science. For example, I might be what philosophers of science call a scientific realist, which means that I think that one of the proper goals of a scientific theory is to describe the world beyond what we can directly measure and observe, and that sometimes science is successful in doing this. You, on the other hand, might be what philosophers of science call an instrumentalist about theories. You think that science doesn't aim to describe the world beyond the realm of observable phenomena at all. You think that scientific theories are just instruments for helping us organize and predict observable phenomena and the results of experiments. And that's how they should be judged. And we should treat the theoretical parts of our theories as nothing more than useful fictions, or at least be agnostic about their truth. This debate between scientific realists and instrumentalists is one of those big philosophical questions about science. Some version of it goes back to the Greeks. And my point is that either view is compatible with thinking of scientific methodology as a set of tools for neutralizing cognitive biases. I'm not saying that both of these are equally plausible views. All I'm saying is that they're equally compatible with everything I've said about scientific methodology in this podcast. So the takeaway message of this episode is really fairly limited. It doesn't imply much for the big philosophical questions about the nature of science. But it does suggest a certain kind of attitude towards science and the authority of science. It suggests, first of all, that people should be very cautious about relying on their intuitions in judging a scientific issue. Our intuitions are just not reliable. One kid developing autism after a vaccination does not imply that the vaccine was the cause of the autism. But we all know that. The sample size is just too small. What about 6,000 kids? Our intuition tells us that if 6,000 kids develop autism after being vaccinated, that's at least evidence for a strong correlation, right? Wrong. It's evidence, but it's lopsided. It's an incomplete body of data. Think of the Dr. Jones example. When you actually look at a more complete body of data, including background rates of autism, the evidence is clear. There is no statistically significant correlation between vaccination and the development of autism. The number of reported cases of autism has certainly shot up over the past 30 years. But part of this is attributable to changes in diagnostic practices. How much of an increase there's been in the actual prevalence of the condition is still unclear, but there's no evidence that it's linked to vaccinations. Multiple studies from different scientific bodies agree on this conclusion. Now, I know that a lot of people in the anti-vaccine movement resist this conclusion, and there are a lot of conflicted parents who see this as a tug-of-war between equal sides, an anti-vaccine side and a pro-vaccine side. But one of the takeaway messages of this episode should be that the sides are not equal, and we shouldn't view them as equal. Human beings left to their own devices will see correlations where there aren't any, and attribute meaning to correlations that are actually meaningless. The more invested you are in the outcome, the more likely it is that you'll be led into error. Only a proper scientific study can resolve the issue, and when multiple studies converge on the same conclusion, then the rational thing to do, provisionally, is to accept the scientific consensus. We may all have strong intuitions the other way, but once we realize how prone to error we really are, and how scientific methods are designed precisely to avoid these errors, then I think we do have a compelling argument for accepting the authority of science, especially when there is a consensus on the issue among the relevant experts in the mainstream scientific community. Well, that's it for this episode. That was a long one. I'm grateful to those who stayed with me until the end. If you're watching this on YouTube, feel free to leave a comment below. If you're listening or watching this on your computer or iPod, you can view the show notes and leave comments at www.criticalthinkerpodcast.com. In the show notes, I have a bunch of references to books and websites that you might be interested in. Thanks for listening.